Welcome. My name is Samarpita Roy, and in this short lecture, I will take you through the concepts of stoichiometry and kinetics, which form an important part of the environmental biotechnology course. Let's begin with stoichiometry. Stoichiometry describes the quantitative relationship between the reactants and products in a microbial reaction. In the bioreactor image on the slide, you can see that an influent containing compound S at concentration C, noted here as CS, enters the reactor. This compound has a stoichiometric coefficient or yield, which we call YS. When leaving the reactor, the effluent contains products arising from microbial conversions at concentrations Cp, represented by a product yield Yp. Stoichiometry is closely linked to operational cost because it tells us how much substrate is needed for the process. On the other hand, kinetics deals with the rate of reactions, how fast microorganisms grow by consuming substrates, and how quickly products are formed. In the reactor diagram, the influent defines the rate of substrate consumption, while the effluent represents the rate of product formation over time. Therefore, kinetics helps us calculate reactor size and influences capital or investment costs. Both are essential when designing and optimizing a bioprocess. Using stoichiometry, we can describe microbial metabolism as an overall growth reaction. This reaction includes an electron donor and an electron acceptor, forming the redox couple, a carbon source, a nitrogen source, and other nutrients that become part of the biomass. Microorganisms consume these compounds and convert them into biomass and products, such as bicarbonate, water, and protons. Each of these components is associated with a yield factor, a stoichiometric coefficient that indicates how much of that compound is used or produced per unit of biomass formed. We can define yields for the electron donor, carbon source, nitrogen source, and electron acceptor, all expressed as moles of compound per mole of biomass formed. Let's look at an example of nitrifiers, which we talked about earlier. For nitrifiers, a stoichiometric relationship can be obtained to describe that ammonia serves as the electron donor in the catabolic reaction, while oxygen acts as the terminal electron acceptor, producing nitrate. This energy-yielding reaction is then coupled to anabolism, which can also be described in a stoichiometric relationship, where bicarbonate or carbon dioxide serves as the carbon source and ammonium provides nitrogen to form the biomass. The process also produces byproducts such as nitrate, water, and proton. We have earlier learned that the overall microbial metabolism is defined as the sum of the number of times the catabolic reaction is required to produce 1 unit of biomass in the anabolic reaction. In the case of nitrifiers, keeping in mind that the lambda cat value of 14 mole ammonia per mole biomass formed, when we combine these catabolic and anabolic reactions, we get the overall stoichiometry of nitrifier metabolism. In this reaction, 1 mole of ammonia is both the electron donor and nitrogen source, producing biomass and is oxidized to nitrate. 2 moles of oxygen serve as the electron acceptor, which is converted to water. And for biomass formation, 0.085 moles of carbon dioxide is required as the carbon source, along with a small amount of ammonia as the nitrogen source. So ammonia plays a dual role. It's both the electron donor and the nitrogen source. This stoichiometric equation gives us a good understanding of how much ammonia, oxygen, and bicarbonate are needed to produce a certain amount of biomass. A key insight when designing and scaling up a bioprocess.